What if the space race never happened? October 4, 1957, Baikonur Cosmodrome, Kazakhstan. A modified R-7 ballistic missile sits on the launch pad. Inside its nose cone is a metal sphere the size of a beach ball, equipped with radio transmitters and batteries. At 7:28 p.m. Moscow time, the rocket ignites. Flames pour from 30 engines. Within minutes, the sphere reaches orbit, circling the Earth every 96 minutes. Its radio beeps can be heard by anyone with the right equipment. Sputnik, the world's first artificial satellite. The achievement stuns the world and terrifies the United States. If the Soviet Union can put a satellite in orbit, it can deliver a nuclear warhead to any American city. Within months, President Eisenhower creates NASA. The space race begins. Over the next 12 years, the United States and Soviet Union will pour billions into competing programs. Satellites, probes, animals, and eventually humans will be launched into space. In July 1969, Neil Armstrong will step onto the moon, declaring it one small step for man, one giant leap for mankind. The space race transformed technology, science, and culture, and gave us satellite communications, GPS, weather forecasting, and countless other innovations. It inspired generations to pursue science and engineering. It redefined what humanity could achieve, and it reshaped the Cold War, providing a peaceful, albeit competitive, arena for superpower rivalry. But the space race was not inevitable. Sputnik was the result of specific decisions by Soviet leadership, driven by military and propaganda considerations. The American response was shaped by fear, national pride, and political calculation. The enormous investments required competed with other priorities: social programs, military spending, infrastructure. At multiple points, leaders on both sides questioned whether the costs were justified. What if the space race never happened? What if Sputnik was never launched? Or what if it was launched, but the American response was different, less driven by fear and competition? What if the vast resources devoted to reaching the moon had been directed elsewhere? How would technology have developed? How would the Cold War have unfolded? And what would our world look like today without the legacy of humanity's greatest technological competition? This is a story about more than rockets and astronauts. It's about how competition drives innovation, how fear shapes policy, and how the absence of a single grand project can alter the trajectory of an entire civilization. Let's explore the world where humanity stayed closer to Earth. For the space race to never happen, one of two things must change. Either the Soviet Union never launches Sputnik, or the United States never treats it as a crisis requiring a massive response. Let's explore the second scenario, as it's more plausible and has clearer consequences. In our timeline, Sputnik caused panic in America. Media coverage was sensational. Politicians, particularly Democrats, seeking to attack the Eisenhower administration portrayed it as proof that America was falling behind the Soviet Union. The missile gap became a political issue. Eisenhower, despite his private skepticism about some space initiatives, felt compelled to respond. NASA was created in July 1958. The space race was on. But Eisenhower was a fiscal conservative who worried about military spending and deficits. He was skeptical of grand gestures, and he had advisors who questioned whether competing with the Soviets in space was wise. What if Eisenhower and his successors had taken a different approach? In this alternate timeline, Sputnik is launched in October 1957. The Soviet Union celebrates, but President Eisenhower's response is measured. He acknowledges the achievement, but frames it as a scientific accomplishment, not a military threat. He notes that the United States already has robust missile and satellite programs through the military. He argues that there's no need for a separate civilian space agency or a crash program to match Soviet achievements. This approach faces political resistance. Democrats attack Eisenhower as complacent. John F. Kennedy, campaigning in 1960, promises to close the missile gap and restore American prestige. But Eisenhower's calm response resonates with much of the public. Americans are concerned about Sputnik, but also about taxes, schools, and economic growth. A measured approach to space, focused on practical applications rather than prestige, gains support. Kennedy wins the 1960 election narrowly, as in our timeline, But without the intense space race context, his famous May 1961 speech doesn't happen. Instead of declaring a goal of landing on the moon before the decade ends, Kennedy emphasizes practical space applications: communication satellites, weather satellites, reconnaissance satellites. NASA exists, but it's smaller, with a budget a fraction of what it became in our timeline. The Soviet Union continues its space program. Yuri Gagarin becomes the first human in space in April 1961, as in our timeline. The Soviets celebrate this as proof of communism's superiority. But the American response is again measured. Kennedy congratulates the Soviets, announces plans for American manned spaceflight, but doesn't commit to a moon race. The focus is on building capabilities gradually, not on dramatic gestures. By the mid-1960s, both superpowers have modest space programs. Satellites are being launched for military and civilian purposes. A few astronauts and cosmonauts have flown brief missions. But there's no race to the moon. No Apollo program consuming 5% of the federal budget. No massive investment in rockets, computers, and engineering. And this has enormous consequences. In our timeline, the space race drove technological innovation across multiple fields. The Apollo program required advances in computing, materials science, telecommunications, and miniaturization. Technologies developed for space found applications in medicine, consumer electronics, and industry. The integrated circuit, while invented before Apollo, was refined and mass-produced, largely because NASA needed compact, reliable computers. Satellite technology enabled global communications and navigation. The space race accelerated technological development by a decade or more in certain areas. But in this alternate timeline, without the space race, technological development follows a different path. Progress still occurs, but it's slower, more organic, driven by commercial and military needs rather than the urgency of reaching the moon. Computing advances, but more gradually. In our timeline, computers evolved rapidly in the 1960s, driven partly by Apollo's need for compact guidance systems. In this timeline, computers remain larger and more expensive longer. The miniaturization push that led to personal computers in the 1970s is delayed. By the mid-1980s, when personal computers are common in our timeline, they're just beginning to enter homes in this alternate world. The tech revolution is delayed by roughly a decade. Satellite technology also develops more slowly. Communications satellites exist, but are fewer in number and less sophisticated. Television remains primarily terrestrial. Transcontinental calls are expensive. Global positioning, which relies on a network of satellites, isn't developed until much later. GPS, which became available in our timeline in the 1990s, doesn't exist in this timeline until the 2010s. Materials science, particularly advanced polymers and ceramics developed for spacecraft, advances more slowly. Medical technologies that relied on space-derived innovations, such as certain imaging techniques and heart monitors, appear later. But the slower technological pace has some benefits. Without the pressure of the space race, development is more considered, more focused on sustainability and civilian applications, rather than achieving dramatic firsts. Technologies, when they arrive, are often more mature and practical. The computer revolution, when it comes in the 1990s, is less disruptive because society has more time to adapt. By the early 21st century, technology in this timeline is roughly a decade behind ours in computing and communications, but it's also more evenly distributed. The focus on practical applications rather than prestige projects has meant more investment in infrastructure, education, and commercial innovation. In our timeline, the space race provided a relatively peaceful outlet for Cold War competition. Instead of fighting each other directly, the United States and Soviet Union competed to achieve first in space, first satellite, first human in space, first spacewalk, first moon landing. This competition absorbed enormous resources, but also created a sense of shared human achievement. The space race humanized the Soviets to Americans and vice versa. It created moments of cooperation, such as the Apollo-Soyuz mission in 1975. But in this alternate timeline, without the space race, Cold War competition takes different forms. Some are more dangerous, others are more productive. Let's examine how the Cold War unfolds differently. First, military spending is higher. Without billions going to NASA and civilian space programs, more money goes to conventional and nuclear forces. The arms race intensifies. By the 1970s, both superpowers have larger nuclear arsenals than in our timeline. The Cuban Missile Crisis of 1962 occurs similarly, but without the context of space cooperation, it's even more tense. Second, proxy wars are more intense. Vietnam, which in our timeline was America's longest and most divisive war, is even larger in this timeline. Without the space race providing an alternative arena for demonstrating American power and ingenuity, more emphasis is placed on winning in Vietnam. American troop levels peak at over 600,000, compared to about 540,000 in our timeline. The war lasts longer and costs more in lives and treasure. Similarly, Soviet involvement in Afghanistan in the 1980s is more aggressive. Without space cooperation providing any softening of relations, the Cold War remains intensely confrontational. But there's also more focus on domestic competition. Both superpowers try to prove their systems superior through economic performance and quality of life. In the United States, this leads to greater investment in infrastructure, education, and social programs. The interstate highway system is expanded more extensively. Public universities receive more funding. Healthcare reforms occur earlier. In the Soviet Union, there's also more focus on improving living standards, though with limited success given the fundamental inefficiencies of the planned economy. But the absence of space race spending means more resources for consumer goods and housing. By the 1980s, the Cold War remains intense but is shifting. The Soviet Union, despite not having the additional burden of competing in space, is still economically stagnant. Mikhail Gorbachev comes to power in 1985 and introduces reforms. As in our timeline, the Berlin Wall falls in 1989. The Soviet Union dissolves in 1991. The Cold War ends not with space cooperation symbolizing détente, but with the simple exhaustion and collapse of the Soviet system. The United States emerges victorious, but it's a more militarized, less technologically advanced superpower than in our timeline. Perhaps the most significant difference in this timeline is the limited development of satellite technology. In our timeline, satellites revolutionized communications, navigation, weather forecasting, and surveillance. They enabled global television broadcasts, intercontinental telephony, and eventually the Internet as we know it. By the 21st century, modern civilization depends on satellites. But in this alternate timeline, satellite technology develops much more slowly. Without the space race driving innovation, satellites remain expensive and are launched primarily for military purposes. By 2000, there are fewer than 200 satellites in orbit, compared to thousands in our timeline. Communications remain more regionalized. Television is broadcast terrestrially, cable and fiber optic networks are more extensive because they are the primary way to transmit signals. The Internet, which emerges in the 1990s, as in our timeline, develops differently. Without satellites providing global connectivity, the Internet is more fragmented, organized around regional hubs connected by undersea cables and ground networks. This has cultural implications. In our timeline, satellite television and the Internet enabled global culture. People anywhere can watch the same shows, access the same information. In this alternate timeline, culture remains more regional. European media differs significantly from American, Asian, from African. There's less homogenization, but also less interconnectedness. Navigation is more challenging. Without GPS, people rely on maps, compasses, and local knowledge. Commercial aviation requires more sophisticated ground-based navigation systems. Shipping is less efficient. The logistics revolution that transformed global trade in our timeline, enabled partly by GPS tracking, occurs more slowly in this timeline. Weather forecasting is less accurate. Without weather satellites providing global coverage, forecasters rely on ground stations and aircraft. Hurricane tracking is less precise, leading to more casualties from storms. Climate science develops more slowly because scientists lack comprehensive global data. Surveillance, both governmental and commercial, is less pervasive. Without satellite imagery, governments rely more on aircraft and ground-based intelligence. This provides more privacy, but also makes monitoring environmental changes, illegal activities, and military movements more difficult. By the early 21st century, the lack of extensive satellite coverage is one of these most noticeable differences between this timeline and ours. The world is less connected, less monitored, and in some ways less advanced. In our timeline, 12 humans walked on the moon between 1969 and 1972. The moon landings were humanity's greatest technological achievement, inspiring millions and demonstrating what cooperation and determination could accomplish. The images of Earth from the moon, particularly the blue marble photograph, shaped environmental consciousness and a sense of global unity. In this alternate timeline, no human has set foot on the moon. Robotic probes have visited, as both the United States and Soviet Union sent unmanned missions in the 1960s and 70s. But the moon remains a distant object, observed through telescopes, not a place humans have explored. This has psychological and cultural effects. In our timeline, the moon landings proved that humanity could achieve the seemingly impossible. They inspired generations to pursue science and engineering. They created a sense of limitless potential. In this timeline, without that inspiration, attitudes toward technology and exploration are different. There's more skepticism about grand projects, more focus on practical, incremental improvements. The belief that we can do anything is weaker. Instead, there's a more modest, realistic sense of human capabilities. Environmental consciousness develops differently. Without the powerful images of Earth from space showing its fragility and isolation, environmental movements rely on other imagery and arguments. Earth Day is still founded in 1970, but the movement is less globally oriented, more focused on local issues. Science fiction is different. In our timeline, the moon landings inspired countless stories about space exploration, many optimistic about humanity's future in space. In this timeline, science fiction is less space-focused, more concerned with Earth-based scenarios, dystopias, social commentary, technological caution. By the early 21st century, the moon is still seen as a distant goal, something humanity might achieve someday, but not an immediate priority. There are occasional calls for a moon program, but they're not politically popular. The focus is on solving problems on Earth. By the year 2025, in this alternate timeline, the world is recognizably similar to ours in many ways, but different in key aspects. Let's tour this world and see what it looks like. Technologically, it's about a decade behind our timeline in computing and communications. Personal computers are common, but smartphones are just beginning to become ubiquitous. The devices are less sophisticated, more expensive. The internet exists and is widely used, but it's slower, more fragmented, and less mobile than in our timeline. Social media exists but is less dominant. Without smartphones making constant connectivity possible, people spend less time online. This has social consequences. There's less polarization, less exposure to algorithmic content, but also less connectivity. Social movements still organize, but they rely more on traditional methods. Economically, the world is similar. Globalization has occurred, though slightly less extensively due to weaker logistics networks without GPS. The 2008 financial crisis occurred, though its contours were different. The global economy has recovered, though growth has been slightly slower. Politically, the world is multipolar. The United States is a major power, but less dominant than in our timeline. Without the technological advantages derived from space race innovations, American economic leadership is less pronounced. China has risen, but is also less technologically advanced. Europe is more cohesive, having focused more on economic and political integration rather than space prestige projects. Environmentally, the situation is worse. Without satellite monitoring providing early warnings about climate change, the issue gained political attention later. Carbon emissions continued unchecked longer. By 2025, global temperatures have risen more than 2 degrees Celsius, higher than in our timeline. Climate disasters are more frequent and severe. Space exploration is minimal. There are a few hundred satellites in orbit, mostly for communications and military surveillance. No human has traveled beyond low Earth orbit. The International Space Station doesn't exist. There are occasional robotic missions to other planets, but they're rare and limited in scope. And there's a growing sense that something is missing. A younger generation, aware through historical records and speculative fiction of what might have been, questions whether humanity should have been more ambitious. They look at the challenges facing Earth: climate change, resource depletion, overpopulation, and wonder if solutions might be found beyond the planet. This leads to renewed interest in space. By the 2020s, there are calls for a serious space program, not for prestige but for practical reasons. Mining asteroids for resources, placing solar power stations in orbit, perhaps eventually establishing colonies on other worlds as insurance against catastrophe on Earth. In 2020, a coalition of nations, private companies, and advocacy groups forms the Global Space Initiative. Their goal is to launch a comprehensive space program focused on practical applications and long-term human presence beyond Earth. They argue that humanity's focus on terrestrial concerns for the past 60 years, while understandable, has left civilization vulnerable to existential risks. The initiative gains support, particularly among younger people and in countries that feel left behind by terrestrial economic competition. China, India, Brazil, and several African nations see space as an area where they can lead. The United States and Europe are more skeptical, given their focus on addressing climate change and social issues, but they don't want to be left behind. By 2022, the first new major space launches in decades occur. Not government programs, but privately funded missions, supported by international consortiums. The goal is to establish infrastructure, more satellites for communications and Earth observation, space stations for research and manufacturing, robotic systems for asteroid mining. Progress is rapid. With modern technology, many things that were difficult in the 1960s are now easier. Reusable rockets, developed partly from military missile technology, make launches cheaper. Autonomous systems handle many tasks that required astronauts in our timeline. By 2025, there are plans for the first human mission to the Moon in over 60 years, not to plant a flag, but to establish a permanent base. The mission is scheduled for 2028. It's a joint effort involving multiple nations and private companies. The goal is resource extraction and scientific research, not prestige. Public reaction is mixed. Some are excited, seeing this as humanity finally fulfilling its potential. Others are critical, arguing that resources should be spent on Earth's problems. Climate activists in particular question whether space exploration is a distraction from the urgent need to address environmental catastrophe. The debate intensifies through 2025, and then in September, something happens that changes the calculus. On September 15, 2025, an automated probe sent by the Chinese Space Agency to survey near-Earth asteroids for mining potential makes an unexpected discovery. One asteroid, designated 2025 Rs-14, has an unusual composition. Spectroscopic analysis reveals concentrations of rare Earth elements far higher than anything found on Earth. The asteroid is relatively small, about half a kilometer in diameter, but if its composition is uniform, it contains more rare Earth elements than all known terrestrial reserves combined. Rare Earth elements are critical for modern technology: smartphones, electric vehicles, wind turbines, advanced weapons systems. China currently dominates the terrestrial rare earth market, and extraction is environmentally destructive. If the asteroid could be mined, it would provide enough rare earths to supply global demand for decades while eliminating the need for destructive mining on Earth. The discovery is announced in early October. It's a sensation. Overnight, the Global Space Initiative gains credibility and urgency. Nations and companies race to develop plans for mining the asteroid. The estimated value of its resources is in the trillions of dollars. But there's a problem. No existing technology can efficiently mine an asteroid and return the materials to Earth. New spacecraft, mining equipment, and processing facilities need to be developed. This requires massive investment and international cooperation, or it requires competition, with multiple actors racing to be first. Within weeks, 3 competing plans emerge. The Global Space Initiative proposes an international consortium, sharing costs and benefits. China proposes a national program, arguing it discovered the asteroid and should have primary rights. And a coalition of private companies, primarily American and European, proposes a commercial approach, with ownership going to whoever can exploit the resource first. The United Nations convenes emergency sessions to establish a legal framework for asteroid mining. The Outer Space Treaty of 1967, which in our timeline was shaped by space race-era concerns, exists in this timeline but is less comprehensive. It forbids national appropriation of celestial bodies, but is vague about resource extraction. Negotiations are contentious. Developing nations argue that space resources are the common heritage of mankind and should benefit all. Developed nations and private companies argue for a finders keepers approach, saying those who take the risks should reap the rewards. China argues for a middle ground, with international regulation, but recognition of the rights of discoverers. By December 2025, no agreement has been reached, and tensions are rising. Multiple nations and entities are proceeding with their own plans to reach the asteroid, which orbital mechanics place within reach in late 2027. In January 2026, China announces it will launch a mission to the asteroid in December 2026, with a goal of landing robotic mining equipment by mid-2027. The mission is called Kwangshan, meaning mining mountain. Within days, the United States announces its own mission, a public-private partnership between NASA and SpaceX, scheduled to launch in early 2027. The European Union and India announce a joint mission. Russia, seeking to restore its space prestige, announces plans for a mission as well. Suddenly, after 60 years of minimal space activity, there's a race. But it's not a space race driven by Cold War rivalry and prestige. It's a race driven by economics and resource competition. The prize is not national glory, but trillions of dollars in rare earth elements. The next 18 months see unprecedented activity. Launch facilities that were underutilized for decades are operating at capacity. Engineers work around the clock, designing mining equipment that can function in microgravity. International diplomats continue arguing about legal frameworks, even as missions are being prepared. Public interest is intense. After decades of viewing space as irrelevant to daily life, people are fascinated by the competition and the stakes. Media coverage is extensive. The various missions are followed with the kind of attention that in our timeline was devoted to the original space race. But there are also concerns. Some warn that a rush to exploit space resources without proper regulation could lead to conflict. If multiple missions reach the asteroid simultaneously, who has priority? What if accidents occur? What if one nation uses force to prevent others from accessing the asteroid? The United Nations attempts to establish a framework before the missions arrive. In June 2026, after months of negotiation, a treaty is proposed. It would establish an International Space Resource Authority, similar to the International Seabed Authority, to regulate asteroid mining. Resources would be shared through royalties paid to the authority and distributed to developing nations. But the treaty faces resistance. China and several other nations refuse to ratify it, arguing it infringes on their sovereignty. Private companies lobby against it, seeing it as a burden on commercial activity. By the end of 2026, the treaty has not been ratified, and the missions proceed. By mid-2027, 4 missions have reached the asteroid. China's Kwangshan arrived first in May. The American SpaceX mission arrived in June. The European-Indian mission arrived in July. Russia's mission, delayed by technical issues, arrived in August. Each mission has placed equipment on the asteroid's surface or in orbit around it. The Chinese have deployed robotic drilling equipment. The Americans have surveying satellites and landing craft. The Europeans and Indians have scientific instruments. The Russians have a small crew of cosmonauts in a capsule nearby, able to oversee operations directly. The asteroid, now referred to as Treasure Mountain by the media, is crowded. Spacecraft from different nations orbit within kilometers of each other. Equipment operates in close proximity on the surface. There are no established protocols for traffic control or resource allocation. In early September 2027, the first incident occurs. A Chinese drilling operation sends debris into space. Some of this debris strikes an American satellite, damaging its communications array. The United States claims this was deliberate sabotage. China insists it was an accident and offers to compensate. Tensions rise. Each nation instructs its mission to take precautions against further incidents. Some missions begin taking more aggressive positions, attempting to establish priority over certain areas of the asteroid. On September 23, 2027, a more serious incident occurs. A Russian cosmonaut conducting a spacewalk to inspect equipment approaches a Chinese drilling site. Chinese Mission Control, interpreting this as an attempt to interfere with their operation, activates a robotic arm that pushes the cosmonaut away. The cosmonaut is not seriously injured, but is briefly out of control before recovering. Russia lodges a formal protest at the United Nations, accusing China of attacking its personnel. China argues it was defending its property. The United States and Europe support Russia, demanding China cease aggressive actions. China refuses, arguing it has the right to defend its mission. By early October, the situation at the asteroid is extremely tense. Multiple nations have military assets watching the situation from Earth and from spacecraft in the vicinity. There's talk of sending armed security personnel to protect operations. Some suggest that if mining equipment is attacked or disabled, it could constitute an act of war. The United Nations Security Council holds emergency sessions. The Secretary General pleads for all parties to step back, to negotiate a framework for sharing the asteroid's resources. But discussions are deadlocked. Each nation feels it has invested heavily and has rights to the resources. None is willing to cede advantage to others. On October 15, 2027, exactly 70 years after Sputnik was launched in our timeline, a meeting is convened in Geneva. Representatives from all nations with missions at the asteroid attend, along with UN officials and representatives from developing nations without space capabilities. The meeting lasts 3 days. It's the most important negotiation about space in human history. The question is straightforward. Will nations cooperate or compete? Will the asteroid's resources be shared or fought over? Will humanity's renewed push into space be collaborative or confrontational? On the third day, October 18th, the negotiators emerge. They announce that an agreement has been reached in principle. The asteroid will be divided into zones, with each mission allocated specific areas to mine. Resources extracted will be subject to a royalty paid to an international fund. The fund will support space development in poorer nations and fund public goods like space debris tracking and safety systems. It's not a perfect agreement. China receives the largest zone, reflecting its first arrival. The United States, Europe, India, and Russia receive smaller zones. Private companies are required to operate under national licenses. Developing nations receive less than they wanted, but gain a stake in space resources for the first time. The agreement is hailed as a breakthrough, signed in a ceremony at the United Nations on November 1, 2027. The media calls it the Treasure Mountain Treaty. Optimists see it as the beginning of a new era of space cooperation. Skeptics warn that implementation will be difficult and that future conflicts over space resources are inevitable. Mining begins under the new framework. By 2028, rare earth elements are being extracted and returned to Earth. The first shipment, arriving in March 2028, contains enough materials to supply global demand for months. The impact on rare earth prices is immediate and significant. By 2030, asteroid mining is an established industry. Multiple asteroids are being surveyed and mined. The economics of space are changing. Launch costs have dropped dramatically with increased activity. Space-based manufacturing is beginning. Plans for permanent human habitats in space are being developed. And there's renewed talk of the Moon, not as a prestige project, but as a strategic location for space industry. The Moon's resources, particularly water ice and polar craters, can support space operations. Its position makes it a natural waypoint for missions to asteroids and eventually to Mars. As the year 2030 begins, humanity finds itself at a crossroads. For 70 years, from the launch of Sputnik in our timeline to 2027, humanity largely stayed close to Earth. Space was an afterthought, curiosity, not a priority. But the discovery of Treasure Mountain has changed everything. Space is now seen as essential to Earth's future, a source of resources and perhaps eventually a home for millions of people. But there are fundamental questions. Will space development be cooperative or competitive? Will it benefit all humanity or only the wealthy and powerful? Will the resources of space be used to solve Earth's problems, or will they create new inequalities and conflicts? The Treasure Mountain Treaty provided a framework, but it's fragile. Already there are disputes over interpretation and implementation. Some nations are pushing for renegotiation, seeking larger shares. Private companies are lobbying to reduce royalties and regulations. Developing nations are demanding more benefits. And there are new challenges. As humans spend more time in space, questions arise about governance. Who has jurisdiction over space habitats? Who makes and enforces laws? The Outer Space Treaty says no nation can claim sovereignty over celestial bodies, but it doesn't address the rights of individuals and companies operating there. Environmental concerns are also emerging. Asteroid mining, if done carelessly, could create debris fields, hazardous to spacecraft. There are calls for environmental impact assessments and sustainability standards, but enforcement is difficult in the vastness of space. And there are ethical questions. If humans establish permanent settlements on the Moon or Mars, what rights do those settlers have? Can they declare independence? What obligations do they owe to Earth? These questions, which seem distant, may become urgent within decades as space settlements move from concept to reality. On March 10, 2030, a joint announcement is made by the Chinese Space Agency, NASA, the European Space Agency, and Roscosmos. They reveal that they have been coordinating planning for a permanent lunar base. The base, to be called Selene Station, will be established in the Moon's south polar region, near water ice deposits. Construction will begin in 2032, with the first crew arriving in 2034. The announcement is accompanied by a call for international participation. Any nation or organization willing to contribute resources or expertise is invited to join. The goal is to make Selene Station a truly international project, a symbol of cooperation and a practical platform for further space development. The reaction is mixed. Many see it as an inspiring goal, proof that humanity can work together. The announcement generates enthusiasm reminiscent of the original space race, but directed toward cooperation rather than competition. Applications to join the program pour in from dozens of countries. But there are also skeptics and critics. Some argue that the resources would be better spent on Earth, addressing climate change, poverty, and inequality. Environmental activists point out that even with asteroid mining providing resources, Earth's fundamental challenges haven't been solved. Space, they argue, is a distraction from the urgent work of saving the planet. There are also concerns about militarization. The Outer Space Treaty forbids placing weapons of mass destruction in space, but conventional weapons aren't prohibited. As valuable infrastructure accumulates in space, there are fears that it could become a battlefield. Already, some nations are developing anti-satellite weapons and space-based surveillance systems. Critics warn that without stronger international agreements, space could become an arena of conflict. And there are questions about who will benefit. Will space development enrich all humanity or create new oligarchies? Will space resources be used to improve life on Earth or to escape Earth's problems? Will the opportunities of space be accessible to everyone or only to the wealthy and privileged? As debates rage, planning for Selene Station continues. By mid-2030, over 40 nations and numerous private entities have joined the project. The budget is unprecedented, dwarfing any single space program in history. But it's distributed among many participants, making it more affordable than the Apollo program was for the United States alone. Construction materials are being manufactured on Earth and in space. Robotic systems are being tested. Astronauts are training. The world watches with anticipation and anxiety. This is humanity's most ambitious project since the original space race that never was. And then, in late 2030, a revelation threatens to upend everything. On November 20, 2030, a research team analyzing data from lunar probes makes an unexpected discovery. Deep scans of the South Polar region, where Selene Station is to be built, reveal something unusual. Beneath the surface, there are cavities, lava tubes, that are larger and more extensive than expected. This is interesting for the lunar base, as these tubes could provide natural radiation shielding. But there's something else. In one of the largest tubes, instruments detect anomalies. The signature suggests artificial structures, geometric shapes that couldn't form naturally. At first, scientists think it's a data error or a false positive. But repeated scans confirm it. There's something in the lunar lava tube, something that appears to be built, not natural. The discovery is kept secret while it's verified. Only a handful of scientists and officials know. By December, the evidence is overwhelming. There are structures in the lava tube, and they're old. Dating of surrounding materials suggests they're millions of years old. On January 5, 2031, the discovery is leaked to the media. Within hours, it's global news. The headlines are sensational: ancient base found on the moon. Evidence of extraterrestrial civilization. Who built the lunar structures? Governments scramble to respond. The official statement is cautious. Unusual structures have been detected, but their origin is uncertain. They could be natural formations that appear artificial, or they could be the result of unknown geological processes. But privately, officials admit they don't have an explanation. The structures appear to be built. The implications are staggering. If confirmed, it would mean that an advanced civilization existed in our solar system millions of years ago. Were they extraterrestrials, or a previous terrestrial civilization that left no other trace? Why did they build on the moon? What happened to them? The discovery dominates every conversation, every news cycle. Scientists debate the evidence. Religious leaders grapple with theological implications. Philosophers discuss what it means for humanity's place in the universe. Conspiracy theorists claim governments have known about the structures for decades. And space agencies face a critical decision. Selene Station is planned for the South Polar region, near the lava tubes where the structures were found. Should the station still be built there, or should that area be preserved for scientific study? If it's preserved, alternative locations for the station will be less ideal, more expensive, and slower to develop. There's also the question of access. Who decides who gets to study the structures? Should it be an international scientific team, or will national space agencies compete to be first? Already, some nations are accelerating plans to send missions to the moon, wanting to see the structures before others. The Selene Station Consortium holds emergency meetings in late January 2031. The debates are intense. Some argue that the discovery makes the lunar base even more important as a platform for studying the structures. Others argue that building near the structures would be irresponsible, potentially damaging irreplaceable evidence. On February 10, 2031, the consortium announces its decision. Selene Station will be relocated to an alternative site. The South Polar region with the structures will be designated an International Lunar Heritage Site, off-limits to development. A dedicated scientific mission will be sent to study the structures with an international team of researchers. But the decision doesn't end the controversy. Some nations, particularly China and Russia, are developing independent lunar missions. They announce plans to send their own exploratory missions to the structures, claiming they're not bound by the consortium's decision since the moon isn't subject to national ownership. The United States and Europe warn that unilateral missions could damage the site or compromise scientific study. They call for all missions to be coordinated through the United Nations. But enforcement is unclear. How do you prevent a nation from sending a mission to the moon? As February ends, multiple missions are being prepared. China plans to launch in April, Russia in May. The International Consortium's scientific mission isn't scheduled until July. There's a race to be first to the lunar structures. And underlying all the planning and politics is a deeper question. Who built the structures? Why? What happened to them? And what will humanity find when we finally explore them? For 70 years, humanity largely ignored space. We focused on Earth, on its problems and possibilities. But a single discovery has changed everything. The moon, which seemed like a barren rock, may hold the key to understanding our place in the cosmos. The space race that never happened in the 1960s is happening now, in the 2030s. But it's not about prestige or ideology. It's about understanding who we are, whether we're alone, and what came before us. The first mission to the lunar structures launches in April 2031. The crew includes scientists from multiple nations. They carry equipment to scan, analyze, and possibly enter the structures. What will they find? Evidence of an ancient extraterrestrial civilization? Proof of a forgotten human predecessor? Something else entirely? The world waits, and for the first time in over 70 years, every eye is turned towards space. In our timeline, the space race happened, and it took us to the moon and inspired generations. In this alternate timeline, the space race was delayed for 70 years, but now it's here, driven not by competition between superpowers, but by the most fundamental question of all: are we alone? The mission launches on April 15, 2031. The journey to the moon takes 3 days. By April 18th, the crew enters orbit. On April 19th, they prepare to descend to the surface near the lava tubes. And as the world watches, as billions of people hold their breath, the mission begins its final approach. What they find will determine not just what we know about the past, but what we imagine about the future. The landing is scheduled for April 20th, 2031, and when the crew makes contact with what lies beneath the lunar surface, everything humanity thought it knew about its place in the universe will change. The broadcast is set to begin at noon GMT, and we will all be watching. The space race that never happened has finally begun, and this time the stakes are not just national pride or technological supremacy. This time, we're racing to understand who built the structures on the moon and whether they're coming back.